Dissymmetry and optical activity. Dissymmetry is the property of non-superimposability on its mirror image, and a dissymmetric molecule may have a simple axis symmetry, yet it will be optically active. Dissymmetry means having only rotational axis symmetry Cn, where n greater than 1. There is no second order symmetry. That is second order symmetries, planar symmetry and centrosymmetry, POS and COS. POS is planar symmetry and COS is centrosymmetry. Dissymmetrical object lack a particular element of symmetry called improper axis of rotation, but they may or may not have other elements of symmetry. Dissymmetric molecule lack improper axis of rotation, that is Sn. Both asymmetric and dissymmetric molecules are optically active, but asymmetric molecules are necessarily optically active. Dissymmetry means a lack or deficiency of symmetry. If POS and COS are absent, the molecule is dissymmetric. Asymmetric molecules are chiral and optically active, but optical activity does not mean that all symmetry elements are absent. If POS and COS are absent, the molecule is optically active. An asymmetrical object or an object that lacks any element of symmetry are chiral, but not vice versa. All chiral molecules are not asymmetric. A dissymmetrical molecule is not always chiral, but a chiral molecule is always dissymmetric. A dissymmetric molecule is not always chiral, but a chiral molecule is always dissymmetric, but not always asymmetric. All improper rotation, including a centrosymmetry and a planar symmetry, convert a left-handed object into a right-handed object. Improper axis of rotation, it is rotation reflection axis. When a molecule and its mirror image is non-superimposable, it is potentially optically active. Since a rotation followed by a reflection, that is a combined operation, always converts a right-handed object into a left-handed object, and Sn axis guarantees that a molecule cannot exist in separate left and right-handed forms. All improper rotation axis Sn, including a mirror plane and a centrosymmetry. Okay, sigma is equal to S1, I is equal to S2. Why sigma is equal to S1? S1 is C1 sigma. When this C1 is operating on XYZ coordinates, it becomes XYZ. When sigma XY is operating, it becomes XY minus Z. That is S1 is sigma. And why I is equal to S2? S2 is C2 sigma. When C2 is operating on XYZ coordinates, it becomes minus X minus Y Z. When sigma XY is operating on this minus X minus Y Z, it becomes minus X minus Y minus Z. That is equal to I. Hence, I is equal to S2. All improper rotation axes Sn, including a mirror plane and a centrosymmetry, convert a right-handed object into a left-handed object, whereas all proper rotation axes leave a right-handed object unchanged in this respect. Hence, molecules having only proper rotation elements of symmetry can be optically active. All dissymmetric molecules are optically active if improper axis of rotation is absent. Optical activity and chirality are closely related to molecular symmetry. All asymmetric molecules are dissymmetric, but the reverse is not true. all asymmetric molecules are dissymmetric, but all dissymmetric molecules are not asymmetric. There are several terms connecting molecular symmetry and optical activity. Optically active molecules have a dissymmetric molecular structure which lack any secondary element of symmetry, namely an inversion center, a mirror plane, or in general a rotation reflection symmetry axis. This table shows relationship between molecular symmetry and optical activity. First one is the symmetric molecule. If alternating axis of symmetry is present, then simple axis of rotation may or may not be present. The molecule is usually optically inactive. For a dissymmetric molecule, if improper axis of rotation absent or alternating axis of symmetry absent, simple axis of rotation may or may not be present. The molecule is usually active. For an asymmetric molecule, if alternating axis of symmetry absent, simple axis of rotation absent, the molecule is usually optically active. Here, this table shows for a molecule, if Sn is present, the molecule is achiral. For a molecule, if Sn absent, the molecule chiral. Dissymmetric point group C1, Cn, Dn. Non-Cn, the molecule is asymmetric. Here, second molecule is cis-1,2-dimethyl cyclopropane and third one is trans-1,2-dimethyl cyclopropane. These two and 3 are stereoisomers, and the fourth one is non-superimposable mirror image of 3, and molecule 3 is optically active. It is dissymmetric and optically active. It lacks an improper axis of rotation. It possesses a proper axis of rotation C2. C2 passing through midpoint of C1, C2 and C3. This molecule belongs to point group C2, that is trans-1,2-dimethyl cyclopropane belongs to point group C2. In the case of trans-1,2-dimethyl cyclopropane, the molecular configuration contains a simple twofold axis symmetry passing through C3 and midpoint of C1, C2 bond. The molecule belongs to C2 point group. HC3 bond is perpendicular to the plane of the molecule and there is no alternating axis of symmetry. Object and mirror image relationship are there and the molecule is dissymmetric and optically active.